Okay, so let's continue. So we have our CGC field, which we kind of reduce to something that is expressed in terms of a row, a two-dimensional color charge density, but we haven't yet specified what this is. Okay, so of course the row, it's supposed to kind of represent the color charge density from valence quarks or that kind of degrees of freedom. So ultimately it is something that is non-perturbative. I'm not going to be able to calculate rho from a weak coupling perturbative QCD calculation. You might be able to calculate it on the lattice in some way or with some models. So you're going to need some kind of models. And then, so let us introduce the MV or Maclaurin-Venneau-Gopalan model. So this is, again, as the name says, it's a model. It's not a first principles QCD calculation, but it's a very reasonable model that has the advantage that it allows you to calculate. It has an explicit model formulated in terms of, in the end, one single phenomenological parameter that has many reasonable physical assumptions built in, works very well, allows you to calculate a lot of things. So that's why it has been very popular. But you have to separate that this is not, it's a model, it's not a first principles QCD calculation, but it's a very useful model that allows you to do a lot of things. Okay. Well, the MV model says that the charge density rho is a stochastic random variable which has which is okay. So now I'm here, over there I separated the x minus dependence from the x-perp dependence. Now I'm going to reintroduce the x minus dependence into the charge density. Okay, so if I just write rho, it might be a function of x-perp, x minus, or just of x-perp. If I write explicitly both arguments or just one argument, then it's a function of both or one. Always with this assumption that, okay, there's kind of a delta function. The x minus dependence is delta function like, okay? So it's a random stochastic variable, and it is local in both x minus and x-perp, okay? And it's a Gaussian variable, which one could, it's interesting to think about how much this Gaussianity actually really matters. I somehow, my thinking on this has evolved also. So let's say a Gaussian variable. Gaussian in the following sense that when I'm going to calculate values that of correlation function rho A, color component A, rho B of y perp and y minus is g squared mu squared x minus delta function of x minus minus y minus and a delta two-dimensional delta function of x perp minus y perp. Okay, so these delta functions are local in x minus, local in x perp, and then there's some unknown function mu squared. In my convention, different people have different conventions for g. For me, rho is and mu squared is a number density, and therefore there's a coupling g here. But other people put, and you shouldn't be confused with that. Okay, so why do I say it? I say that it only actually has a parameter. Here it looks like there's an arbitrary function, but when we're doing kind of iconal high energy balls, anything that you typically calculate only depends on the integral of this function over x minus. Okay, so this is why, in the end, when the dust settles, there's one unknown parameter which you have to fix to something, and then you have a liquid model for something else. So what is the justification? I think that Yuri Kovtchekov puts it actually quite nicely, that this is a model for in the asymptotically small x limit. This is in the asymptotically large a limit. Okay, so we think that we think that we are in a regime where x is small enough, doesn't need to be asymptotically small, but small enough for the whole picture to make sense. And then we look at a very, very, very large nucleus. And so then if we look at one point on the transverse plane of that nucleus and we go through the nucleus, we are seeing color charges from many, many, many different nucleons that are completely independent of each other. And so at every coordinate, you see a slightly different color charge. There's no, you're looking at going through an infinitely thick nucleus. Move just infinitesimally in the coordinate. At some point during this infinitely long path, there's going to be a nucleus go through in the previous, at the next you will go through now, and so the color charge is different. Okay, so it's a very kind of a minimalistic assumption. Things that are kind of consistent with DGLAB evolution, because this kind of a point-like thing also means that your color charges are kind of like point-like observables. So this gives you power law tails in transverse momentum that of point-like particles. So in some sense, it matches to a physical picture quite nicely. Need any other, and the 1 point expectation value is 0, 2 point expectation value is given by this, and if for some reason you need a higher point correlator, the higher point, the fact Gaussian tells you how you get higher point correlators in terms of the 2 point correlator. Okay. So now this is a very convenient model that allows you to calculate things, okay? So let's look at a kind of the simplest possible thing that you would calculate from this. So let's calculate the dipole amplitude, which you remember from yesterday and from the hybrid formalism. Okay, so let's calculate what I call S, which is a function of R, which is x perp minus y perp, equals 1 over NC, then average in B model sense of a trace of 2 Wilson lines at x perp and V dagger at y perp, like this. This is the thing that appeared in the hybrid model. We could calculate, well, yeah. So this is kind of the easiest thing to calculate in the MV model. And then we recall that now, okay, yes. Then we recall that this V, the Wilson line, is a path-ordered exponential. And now, since we compared to yesterday, we switched. So so path-ordered exponential from minus infinity to plus infinity, dx minus now minus ig, and then what appears is the covariant gauge A. So what is here is rho of, okay, so let me call this A plus covariant at now I can use the x minus, and A plus covariant is 1 over nambla perp squared rho of x minus and x perp. So now I'm keeping the kind of an x minus dependence everywhere because I need to make sense of this path ordered exponential, but all the time in the end we're going to think of this as a kind of a rather delta function like thing. Okay, so I'm not gonna go into inverting this operator yet. Instead, what I will define is that I will say that I have an A plus correlator, so that A plus at x perp and x minus is, and then color index, A plus at color index B, y perp, y minus, like this, is going to, so A plus is linearly proportional to the rho, and I know the rho correlator, so a lot of things just carry over, a lot of things that carry over from here, and I would just say that this is a g squared delta A B. Oh, and of course here, local in color, so delta A B, essential, because the color indices here are A. This is kind of the only kind of gauge invariant or SU3 invariant thing you can write down has two color indices, okay? So g squared delta AB, the same mu squared x minus, and then a delta function in x minus minus y minus times, times some function L of x perp minus y perp, and this function L essentially encodes the physics of this inverse Laplacian. So we can calculate it by Fourier transform back and forth, and we'll do that a little bit later. Let's now just denote that this L. Okay, so plugging this relation into this correlation will give us a correlation function for the A pluses, which are in the exponent. And some parts of that I'm just parameterizing in terms of a function that we'll calculate a little bit later. But we can calculate it based on what is written down here. Okay? No?
You were saying that the delta AB is the only thing you can write in terms of the for SU3 invariance, right? But the mu depends on A. That wouldn't be.
Yeah, so this is why the mu cannot depend on A. So somehow I think the statement here is that if I have has two color indices, and somehow I want this object to be SU3 invariant so that it doesn't prefer any particular direction in color space. Basically, the only thing it can be is some function which has no color index times delta AB. There's no way to make something which is kind of, and this has to be symmetric. There's no way to have a take.
I thought this was an A, but it's not a mu. Oh, mu squared.
Mu squared.
Okay, sorry.
Yeah. Yes. Mu squared. Yeah. Good. So now okay, so now the general strategy. So we have this correlator which goes into the exponent of these Wilson lines, which are these path-ordered exponents. So the general strategy for calculating this kind of expectation values is to discretize the x minus coordinate. And the nice thing about, and that's another way of thinking about what this path ordering means. So there's one way of thinking that this path order, I told you that it's nice to think of this path ordering as a solution defined by the solution to the differential equation. Here, when it is also convenient to think of a path ordered exponential as being a product of a path ordered product of infinitesimally small exponentials. I have an exponential of a integral. If I discretize x minus, my integral becomes a sum. I have an exponential of a sum, which is the product of exponentials, right? And this product of exponentials is ordered because of this path ordering, okay? So what is even nicer is that if here I have a v, so in this v, if my product is ordered from left to right, if I take a v dagger, the product is ordered from right to left, right? So if here in this V, the last value, the largest x minus values are to the right, in here, the same largest x minus values in the V dagger are to the left. So they are next to each other. So kind of so when I discretize this, I take the last, somehow the last point here, the last point, largest x minus value from this is next to the largest x minus value from this, because this is ordered from left to right, this is a dagger, it's ordered from right to left, right? And then I bring my A pluses at the last x minus point there together, right? And then I don't need to worry about the fact that they don't commute because they are together next to each other. I can use this correlator and then somehow use this correlator and then build things up from there. So, okay, so let me try to, I'm gonna try to do this a little bit, a little bit quickly. So let me discretize a little bit quickly, jumping over some intermediate steps. So we're going to discretize. I'm going to say that x minus is some integer number times some delta minus, where delta minus is some infinitesimal parameter. Okay. And now my discretized A plus correlator is I have A plus at n and A plus at n prime and b, okay? And this discretized, I have the same g squared, same delta A b, same mu squared x minus. Now the delta function of x minus minus y minus, if I go to, I want to write it as a discrete thing. Delta function dimensionally, it has dimensions of 1 over the argument, right? So the discrete analog of the delta function is 1 over this infinitesimal step in x minus times a Kronecker delta n prime, right? This is the delta function of x minus minus y minus, okay? And I need to keep consistently counting the powers of this delta minus to get the right thing. And then I have the L of x perp minus y perp, which hopefully we'll come back to in a minute. And then if I plug these, and then I want to discretize this path ordered exponential. So the discretized path ordered exponential is that this V is a product of n going from, let's say, minus capital N to plus capital N exponential or minus I g. I'm discretizing the integral, so d minus, so this is a delta minus from discretizing the integral, and then an a plus whatever, so a plus, let me write the color indices, a, so this is a color matrix, so this is an a plus a ta, okay, and this is an a plus a ta, and this is now this n, right? Okay, so this is a color matrix. I wrote out the color structure. V is an infinite product, or infinite product. I'm going to be taking this capital N to infinity and this delta minus to 0. It's V is an infinite ordered product, and then for these discretized A's, I have this 2-point function. Okay. Okay, so let's, I think I can use this. What the cloud of smoke. Good. Okay, so So then what do we do? I want to write it over here. Then what you do is that then as I said, what you do is that you plug this in here, and then from this infinite product, it's always kind of the latest ones that are next to each other. So I just need to take, let's say, the last one from the V and the last one from the V dagger. They are next to each other. Now my delta is decimal, so I can in this delta minus for one step. So what I'm calculating are expectation values like 1 minus I G delta minus A plus N order minus 1/2 G squared delta minus squared A plus N and then I'm doing the same for the one coming from the V dagger. Okay. Oh, and these are at this is at better. From the other one, I get 1 plus, it's a Hermitian conjugate, I G delta minus A, it's the same N now, Y perp, T Y perp A, T A minus 1/2 T squared plus NA and A plus BNB TA TB. And maybe if you want to be exact, well, I could put this a prime A here to the other ones. Okay, and then plus dot dot dot, which I'm higher orders in delta minus. Okay, so now this is my expectation value that I want to calculate using this. Okay, so first of all, the first term is 1. Okay, 1 times 1. Then I get this 1 times just this one. That's expectation value, so it vanishes, right? My expectation value of 1 times a single A plus is 0. That's the only kind of color neutral thing it can be. And the same thing for this 1 times this single point function. So the single point functions go away because my color expectation value, the expectation value of a single A plus is 0. That's the only thing it can be from the color point of view. Okay, so then I get an expectation value of this times this, okay? So it's minus IG plus IG, so it is plus G squared delta minus squared. I use this expectation value here times another G squared. Then I have a delta AB. Okay, so this is A prime and A, so I have a delta A prime. So the delta AA prime from the expectation value, these TAs and TA prime are from here. I have this mu squared now at this discretized coordinate n minus, and then this here, so this is mu squared depends on this n. Then I have a 1 over delta minus from the discretized delta function. This I've already used. I'm already putting all the n prime to be the same. And then and L of x perp minus y perp. Okay.
So we are doing this averaging immediately. So this after the equality sign is
Ah, we are already absolutely. We already did the average. Thank you. Good. Yes. Yes. So that was this times this. Then the other terms at the same order in delta minus are the square term, where what you see is that first of all there's a minus 1/2. So here there was a this times this gave a plus. This has a minus 1/2. It has the same powers of g, same powers of delta minus. It has similarly a 2-point function, a 2-point correlator of a pluses. But now these are two a pluses at the same point, right? And then I have a Kronecker delta a between delta AB times TB. So this structure is the same. So the expectation value of this term, together with the 1 here, just gives me a minus 1/2 L of x perp minus x perp, right? And then the same thing for this term. It is a minus also y perp minus y, and then a bracket. And this factor multiplying them is the same, okay? Now I can do, and then there are higher orders in delta minus. So you see, time I go to higher order, I get every time I expand more, I get one full power of delta minus, which is infinitesimally small. Together with the delta minus, I also get a power of 1 power of a plus. And because the a plus correlator goes like 1 over delta minus, I can think that kind of my a plus is delta minus. But it doesn't compensate the fact that when I go to expand more, I get integer powers of delta minus divided by the square root. So the higher orders are things that go away when delta minus goes to 0. So I don't need to go any further than this. Okay? Then plus dot dot dot, which I neglect. This, remember at this stage these are still matrices. I haven't taken the trace. This is the now that I have done the expectation value, I generate this Casimir, and now these are still color proportional to the matrix in color space. So the color structure is very trivial now. Okay? And then now I've done this, and now I re-exponentiate. So this is again, I write this as exponential g to the 4th mu n squared here, delta squared and delta minus squared and 1 over delta minus. So this is 1 delta power of delta minus is here. And then I call this combination. So here you see there's a combination of L at this correlation function, which we haven't specified yet, at different coordinates, minus 1/2 the correlation function at 0, minus 1/2 at the correlation function at 0. I will call this minus gamma x perp minus y perp. So this is just another correlation function, which is a linear combination of my previous correlation functions. This is why I didn't calculate this L yet, because I'm just going to calculate gamma directly. Okay, and because I introduced a minus, I want to put a minus here, and gamma of x perp, and then plus higher order in plus order delta minus to the power 3 over 2 parametrically. So plus higher orders that I'm neglecting. And the Casimir, yes, thank you. CF. Okay. And remember, this is still a matrix to the identity matrix in color space. Yes?
I think I don't understand. You have the average of two,
Yep.
and then you split them as products of things. Right? Product of different exponentials.
So I have an average of two fields at locally at x minus. And so fields at different, and which is a delta function x minus. So fields at different values of x minus are uncorrelated with each other. They don't, so the fact that they're uncorrelated means that a expectation value of a product is the same as the product of expectation values. Because all the fields at different x minuses are completely uncorrelated, I can take the expectation values separately for every value of x minus, which is now my discretized to n.
So that's why the correlator of the product of exponentials can be expressed as the product of the correlators.
Yes, yes, yeah, exactly. It's this property. That's one of the somehow the crucial thing that makes the calculation possible. This property that enables us to take the expectation value of such a product and write it as a product of expectation values, because the fields at different x minuses are independent of each other. Good. Good. So now we have a result, and then we just put these together. Now all these things are different. All these things are different. All the things at different x minus kind of exponentiate, and in the end, so in my dipole operator here, I had a 1 over nc times trace, but now that I'm taking the expectation values, what I have here are just identity matrices. So I have 1 over nc times trace of an identity matrix, which is 1. So the 1 over nc trace goes away, and my final result is that my dipole amplitude is exponential of, I have to check that, exponential, and then in the product, I put these kind of infinitesimal exponentials together. So I'm multiplying exponentials, and taking an exponential of the sum. Now these are mute. I don't need to care about path ordering anymore. These are just identity matrices in color space. So I have so the whole thing is an exponential of a sum of this kind of things. This is a sum of things that are proportional to the infinitesimal time step in x minus, infinitesimal step in x minus, which means the exponential of integral. Right? The thing that is in the exponential is infinitesimal step times sum of something. So that's an of an integral. So now I come back to a continuum notation and write this as g to the 4 integral dx minus mu squared x minus from minus infinity to infinity, whatever it is. We know that it's kind of delta function like anyway. And then gamma of x perp minus y perp. Okay? And that's it. So several. So that is our dipole. So let's do a few things to understand a little bit better what this thing is. So first let's calculate this gamma. Okay. Okay. So at each x minus, our a plus is 1 over nabla squared rho, and the rho correlator is a delta function in x perp minus y perp. So you know that to solve kind of an equation you solve it by Fourier transforming. Here I'm going a little bit quick because in the interest of time. So you solve it. So you need to Fourier transform this correlator. Fourier transform of a delta function is going to be a delta function. I'm going to Fourier transform it with respect to both. So what I have is for the Fourier transforms is that the rho correlator, rho k, rho p correlator is proportional to p perp plus k perp, right? And then I Fourier transform this equation. It gives me that a plus as a function of k perp goes like 1 over k perp squared, rho as a function of k perp. So the rho correlator in momentum space, I'm not writing out the factors, plus and rho, so I Fourier transform and Fourier transform back. And remember this gamma correlator was the correlator of a plus, but then I subtracting the value at identity. So cutting short a few steps, I hope that you will believe me if I say that this gamma of x perp minus y perp is can be, so Fourier transforming back and forth, it is going to be a d squared k perp over 2 pi squared d squared p perp over 2 pi squared. And then I have these inverted Laplacians. So I have k perp squared and p perp squared. Then I'm doing Fourier transform. So for the for the part where I had the L at x perp minus y perp, I actually have an exponential of x perp minus. Okay, so exponential x perp k perp plus I y perp dot p perp, and then I have a minus 1, which is kind of because I'm subtracting the same thing where I'm setting x, and I can set x and y to 0. And then here I have a 2 pi squared delta function of p perp plus k perp, which comes rho correlator in coordinate space. Okay. Yeah. Good. So if I can calculate this thing, I can calculate the rho integral. So here, I still don't want to erase. Now I can erase this. So have this integral. So first, of course, I do the 2 pi, the delta function integral. So this gamma of x perp minus y perp is a d squared p perp over 2 pi squared, and then exponential of I p perp dot x perp minus y perp minus 1 over p perp to the 4th, right? So this is completely sick, right? It's completely sick. Especially if you look at this minus 1, which corresponds to this L at value 0, which came from the squares. So this is a very infrared divergent integral. It's d squared p over p perp to the 4th, right? So this contribution individually is very sick. It's power law divergent in the ultraviolet, power law divergent at small p. Luckily, the power law divergence at small p is actually cancelled to a large extent by the fact that this exponential goes to 1 when p perp goes to 0. So the fact that these appear in this combination of exponential of ip times the coordinate difference minus 1 softens the infrared divergence in this operator, in this integral, from a very sick power law to only a log. and what's a log between friends? Okay, so theorists, a log is almost a constant. For some people, in some cases, some parts of particle physics, logs are enormously large, and in some places, logs are kind of just like a constant and don't really matter. And so here, log is kind of like a constant that doesn't really matter. So, and the ultimate reason is that we are here calculating a color singlet expectation value. We are calculating an expectation value of trace V dagger V, which is a color singlet operator. And because we are calculating a color singlet expectation value, the leading very thick divergence cancels, and we are left with something that is much milder. Okay? But I still need to regularize it. If I regularize it with some way, I will get 1 over 8 pi, and then x perp minus y perp squared times a log of 1 over x perp minus y perp times there's some scale in there which I needed to introduce to regularize this. Okay? So this gamma goes like r squared times a log times log r, and then I can plug it. Then I can plug this expression into here. Okay. So then I know what this S looks like. I can plot it. Now I have an explicit expression, and of course it looks like basically just like what we know it should look like. It's going to be some curve like this, where here in the close to 1 it goes like 1 minus r squared log r. Okay. And here it then has some other behavior. This is my S. Of course, from this I know that, okay, I can define the saturation scale. This is 1 over Qs, if this is R. So what is the saturation scale here? Well, basically, here there's an R squared, there's some pi's, and so on. So depending on what you use for the convention, you can see that this is saturation scale. So the exact relation between the saturation scale and the MV model parameter depends on how exactly you define the saturation scale. It depends on what you do with the non-log terms here. What do you do with this log? How do you regularize this integral? So this is why different people have different numerical values for QS, because conventions like this. But overall, we can see basically as advertised, the physics only depend on the integral over x minus of this thing. So in the MV model, we only really have one free parameter, and that parameter is more or less the saturation scale. Okay, so you can think, simplifying things only a little, you can think that the MV model has one parameter, that's the saturation scale. But then, yeah.
How do we get log divergence here? I mean, we have one p from the measure, and when we expand exponential, we also, if we keep only leading term, we get p squared over p to the fourth. This is not orderly.
So okay, so let me do the angular integral here. I don't know if you have, yeah. Oh, okay, yeah. Basically, after an angular over p cubed, yeah, and there's a j0 of pr. Like this, and then from this you can see it's a logarithmically divergent. Good.
Also
the regulator is a parameter. Yes. Well, yes. The regulator is, in some sense, you can say that it's another parameter. You have two parameters: the regulator and mu squared. Good. So that was the MV model. So the nice thing about the MV model is that you can really calculate things. You can really calculate things explicitly. Another thing that I would like to point out here is that this, when you Fourier transform, if you Fourier transform this S to momentum space, at large k perp, it's going to go like 1 over k perp to the 4th. This 1 over k perp to the 4th is kind of like that's a perturbative like behavior, right? And the fact that it goes like a power is related to this log. If you often what people do is that they say that, oh, I don't care about this log, let me just say that the log is 1. And then this power law at large k perp becomes then it becomes really exactly a Gaussian, and a Gaussian Fourier transform is a Gaussian, so then you don't get this power law tail at large kt. And somehow this power law tail at large kt is kind of, the physics that it looks like is that that's what you get if you scatter from point-like color charges. So this power law in k perp really originates from the fact that in the MB model we had this delta function in x perp, which means that the scattering, the color charges are point-like color charges. And it shows up in a cross-section as this k perp squared. And before, I think we're so much over time, but I have one more thing that I will say before we go for lunch, is that so this is kind of so-called dipole distribution. You could also calculate the Weizsäcker-Williams distribution, because we said that we want to go to a light cone gauge in order to be able to count how many gluons there are. So if you really make a bona fide effort to ask the question, how many gluons do I have in my color glass condensate? What the answer to that question is so-called Weizsäcker distribution, which is essentially defined as the 2-point function of these light cone gauge fields. So you take this, it's a V-Dagger derivative V, and you calculate the 2-point function, and you Fourier transform to coordinates momentum space. That would be the best possible answer to the question, what is the distribution of gluons in the color glass condensate? It doesn't mean that it's necessarily the best answer to the question of how do I calculate the cross-section for some process. There are some processes whose cross-section is naturally expressed in terms of the Weizsäcker-Williams distribution, but not all. But nevertheless, this is something that you could calculate. And since the Weizsäcker-Williams, the light cone gauge field explicitly is proportional to 1 over G, right? So the Weizsäcker-Williams distribution will go like 1 over alpha S. Then it has the same Wilson lines. So it's also going to be somehow sensitive to the same saturation scale, right? It's going to have a different functional form slightly, but it's nevertheless going to be 1 over alpha S, and then some function of k perp divided by the saturation scale. This 1 over alpha S is really the justification for why the color glass condensate is a condensate. So the fact that if you really do your best effort to count the number of gluons, the number of gluons will be 1 over alpha S. So this is the reason for the condensate. But I try to stress you, it's not always a good idea to try to count the gluons. Trying to count gluons doesn't necessarily lead you to a calculation of a cross-section. But if you nevertheless do want to count gluons, this is what you do. And so this 2-point function of the light cone gauge fields is a 4-point function of Wilson lines, because there's V-Dagger V and then the other V-Dagger V. So you can calculate it using this same discretization technique. It has been done. It was originally done by Jamal, Jalili, and Marian. I think 97 was the first calculation of this. So it's a calculation that proceeds in a similar way, but it's more complicated. And I think this is everything for today. Alpha S has to be, yeah, but this is a kind of a leading order calculation, so the calculation doesn't tell you what the scale for alpha S is. At the end, you must choose something, yeah. Good, but I think this is it for today, unless there are questions.